There's a reason why every particle accelerator on Earth, no matter how powerful, has never quite reached the speed of light. It's not about needing more energy. Something fundamental happens in that infinitesimal gap between almost light speed and true light speed. Something that would transform you in ways that violate everything we understand about consciousness, time, and reality itself. Today, we're diving deep into one of physics's most fascinating thought experiments. What would happen if you traveled at light speed? If you are fascinated by that very thought, don't forget to subscribe to the channel and give this video a like. Are you ready? Let's get started. The first thing you'd notice as you accelerate toward light speed wouldn't be the scenery rushing past. It would be the complete transformation of time itself around you. Einstein's special theory of relativity, confirmed by countless experiments including precise atomic clock measurements on high-speed aircraft, tells us that time dilation becomes extreme as you approach the cosmic speed limit. At 90% light speed, time would slow down by a factor of about 2.3. This means that for every hour that passes for you, over 2 hours would tick by for everyone back on Earth. But as you push closer to light speed, say 99%, time dilation becomes truly dramatic. Now, for every hour you experience, over 7 hours pass on Earth. Your journey becomes a one-way ticket into the future. But here's where the physics becomes truly mind-bending. As you approach 99.9% light speed, the time dilation factor jumps to over 22. Push to 99.99%, and you're looking at a factor of over 70. The mathematics of relativity shows us that as you get infinitesimally close to light speed, time dilation approaches infinity. In other words, if you could somehow reach exactly light speed, time would essentially stop for you relative to the rest of the universe. The energy requirements for this impossible journey reveal why nature has set this cosmic speed limit. According to Einstein's famous equation E equals mc squared, as your velocity increases, your relativistic mass increases too. The energy needed to accelerate you grows exponentially as you approach light speed. To reach exactly light speed would require infinite energy, more energy than exists in the entire observable universe. The relativistic heavy ion collider and the Large Hadron Collider routinely accelerate particles to over 99.99% light speed, and the energy requirements are staggering. The LHC uses superconducting magnets cooled to colder than outer space and consumes enough electricity to power a small city, all to push protons to near light speed. Scaling this up to accelerate a human being would require energy sources that dwarf anything we can imagine. But let's suspend disbelief for a moment and imagine you've somehow achieved the impossible. As you reach light speed, the universe around you would undergo transformations that challenge the very nature of reality. Length contraction, another consequence of special relativity, would compress the entire universe in your direction of travel to zero thickness. From your perspective, the cosmos would become a flat, two-dimensional plane. The Doppler effect would create a visual spectacle unlike anything ever witnessed. Light from stars ahead of you would be blue-shifted to extreme ultraviolet and X-ray wavelengths, while light from behind would be redshifted into radio waves. The familiar constellations would vanish, replaced by an alien sky painted in impossible colors. The cosmic microwave background radiation, normally invisible to human eyes, would be shifted into visible light, creating a blazing wall of primordial fire in front of you. But here's the most profound implication of traveling at light speed. You would experience no passage of time whatsoever. From your perspective, your journey would be instantaneous, regardless of the distance traveled. You could cross the galaxy, traverse the observable universe, or travel to the edge of space-time itself, and from your viewpoint, no time would pass at all. This creates a paradox that goes to the heart of consciousness and experience. If no time passes for you during the journey, can you truly be said to experience it? Photons of light racing across the cosmos experience no time between emission and absorption. A photon created in the core of a distant star 13 billion years ago and absorbed by your eye right now experiences no duration between those events. From the photon's perspective, its creation and destruction are simultaneous. The implications extend far beyond mere physics into questions about the nature of existence itself. If you could somehow maintain consciousness while traveling at light speed, you would exist in a state outside of time as we understand it. You would become, in a very real sense, eternal, not because you live forever, but because you exist in a realm where forever has no meaning. Recent discoveries in quantum mechanics add another layer of complexity to this thought experiment. Quantum entanglement, demonstrated in experiments that won the 2022 Nobel Prize in Physics, shows us that information can be correlated across vast distances instantaneously. While this doesn't allow faster-than-light communication, it suggests that the universe operates according to principles that transcend our everyday understanding of space and time. As we delve deeper into the impossibility of light-speed travel, we encounter one of the most fascinating aspects of Einstein's relativity: the complete breakdown of simultaneity. At light speed, the concept of now loses all meaning. Events that appear simultaneous to stationary observers would occur at completely different times from your perspective. The birth and death of stars, the formation and evaporation of galaxies, the entire history of the universe would collapse into a single, timeless moment. This isn't just theoretical speculation. Particle physicists working with cosmic ray detectors have observed muons, subatomic particles created when cosmic rays strike Earth's atmosphere, that shouldn't exist long enough to reach the ground. These muons have a lifetime of just 2.2 microseconds, yet they're detected at sea level after traveling through kilometers of atmosphere. How is this possible? From the Moon's perspective, traveling at 99.9% light speed, the atmosphere is length contracted to just a few meters. What seems like an impossible journey to us is a brief hop from the Moon's frame of reference. The visual effects of approaching light speed would create a spectacle that no human eye has ever witnessed. As you accelerate, the aberration of light would cause the entire visible universe to compress into a bright circle directly ahead of you. This phenomenon, called the relativistic searchlight effect, would concentrate all incoming light into an ever-shrinking cone in front of your spacecraft. Stars behind you would seem to swing around to the front, their light bent by your extreme velocity. Computer simulations created by physicists at MIT and the Australian National University have modeled what this would look like. At 90% light speed, the forward view would show significant distortion. At 99%, the entire visible universe would be compressed into a circle about 60 degrees wide. Push to 99.9%, and this cosmic spotlight shrinks to just 12 degrees. At the impossible threshold of light speed itself, all light in the universe would converge to a single, infinitely bright point directly ahead. But the transformation of space and time at light speed creates paradoxes that challenge our understanding of causality itself. The relativity of simultaneity means that events that appear to happen in sequence from one perspective might happen in reverse order from another. At light speed, cause and effect break down entirely. You could, in principle, arrive at your destination before you left, creating grandfather paradox scenarios that physicists still debate today. The energy considerations become even more staggering when we consider realistic spacecraft. The Parker Solar Probe, humanity's fastest spacecraft, reaches speeds of about 430,000 miles per hour. Impressive by human standards, but only 0.06% light speed. To accelerate even a small spacecraft to near light speed would require antimatter engines or other exotic propulsion systems that exist only in theoretical physics papers. Recent experiments at CERN have created and stored antimatter particles, but the quantities are infinitesimal. All the antimatter ever created in human laboratories wouldn't power a light bulb for more than a few minutes. To fuel a light-speed journey would require antimatter factories operating on scales that dwarf our current industrial capacity. Even then, the rocket equation, the tyranny of having to carry your fuel with you, makes the challenge exponentially harder. The biological implications of light-speed travel present another set of seemingly insurmountable challenges. Even at speeds far below light speed, radiation becomes a lethal threat. As you accelerate through space, hydrogen atoms, the most common element in the universe, would impact your spacecraft with the energy of particle beam weapons. At 99.9% light speed, each hydrogen atom would strike with the kinetic energy of a 14 TeV proton beam from the Large Hadron Collider. The interstellar medium, usually considered empty space, would become a deadly radiation field. Cosmic rays would be blue-shifted to extreme energies. The gentle cosmic microwave background would transform into a lethal gamma-ray laser. Without some form of exotic shielding, perhaps using the same physics-defying technology that got you to light speed in the first place, biological organisms would be instantly vaporized. But let's push our thought experiment even further. What if consciousness itself could somehow exist at light speed, divorced from biological constraints? This brings us to one of the deepest questions in physics and philosophy: the nature of information and its relationship to the physical universe. Information theory, developed by Claude Shannon and refined by generations of physicists and computer scientists, tells us that information is physical. It requires energy to create, store, and transmit. The Landauer principle demonstrates that erasing information generates heat, a fundamental connection between information and thermodynamics. At light speed, where time stops, how could information be processed? How could thoughts occur? How could consciousness exist? Some theoretical physicists have speculated about tachyons, hypothetical particles that always travel faster than light. If such particles existed, they would experience time flowing backward and could, in principle, carry information into the past. But decades of searches have found no evidence for tachyons, and their existence would create causality paradoxes that seem to violate the fundamental structure of space-time. The holographic principle, emerging from studies of black hole thermodynamics by Stephen Hawking and others, suggests that all the information in a volume of space can be encoded on its boundary. This profound idea implies that the three-dimensional world we experience might be a projection of information stored on a two-dimensional surface. At light speed, where one spatial dimension collapses to zero, would we be experiencing reality in its more fundamental information-theoretic form? Recent discoveries in quantum mechanics add another layer to this mystery. Quantum superposition allows particles to exist in multiple states simultaneously until observed. The double-slit experiment, confirmed with increasingly large molecules, shows that matter exhibits wave-like properties that defy classical intuition. At light speed, would consciousness itself enter a superposition of states, experiencing multiple realities simultaneously? The many-worlds interpretation of quantum mechanics proposed by Hugh Everett suggests that every quantum event branches the universe into parallel realities. From the perspective of a light-speed traveler experiencing no time, would all possible quantum branches collapse into a single, unified experience? Would you perceive the multiverse as a whole rather than a single timeline? These questions push us to the very limits of human knowledge and perhaps beyond. The intersection of relativity, quantum mechanics, and consciousness remains one of the deepest unsolved problems in science. The fact that traveling at light speed creates such profound paradoxes might be nature's way of telling us that consciousness and light speed are fundamentally incompatible. The cosmic perspective on light speed travel becomes even more profound when we consider what Einstein called the twin paradox. Though at true light speed, it transforms into something far stranger than a mere age difference between siblings. Imagine you have a twin who stays on Earth while you embark on your impossible light-speed journey. From your perspective, the trip is instantaneous. You experience no time whatsoever. But for your Earthbound twin, years, decades, or even millennia pass. you would return to find not just an aged sibling, but potentially a completely transformed world, or perhaps no world at all. This temporal disconnect reveals something fundamental about the nature of existence. We typically think of ourselves as traveling through time at a rate of 1 second per second, but Einstein showed us that we're actually traveling through space-time. The faster you move through space, the slower you move through time. At light speed, all of your motion through space-time is directed through space, leaving no component for movement through time. You become frozen in a single moment while the universe ages around you. The implications for space exploration are both tantalizing and terrifying. If we could somehow approach light speed, the vast distances between stars would become irrelevant from the traveler's perspective. A journey to Proxima Centauri, our nearest stellar neighbor at 4.2 light-years away, would seem instantaneous to you. A voyage to the center of our galaxy, 26,000 light-years distant, would pass in the blink of an eye. You could even attempt to cross the observable universe, a journey of 93 billion light-years, and experience no duration whatsoever. But here's the cosmic catch. While no time passes for you, the universe continues its relentless evolution. Stars are born and die, galaxies collide and merge, and the accelerating expansion of space carries distant objects beyond the cosmic horizon. The universe you return to would be fundamentally different from the one you left, aged by exactly the distance you traveled in light years. Recent observations from the James Webb Space Telescope have given us unprecedented views of the early universe, showing us galaxies as they existed over 13 billion years ago. These ancient structures appear to us because their light has been traveling through space for most of cosmic history. If you could travel at light speed to one of these distant galaxies, you would arrive to find it had aged 13 billion years during your instantaneous journey. The young, vibrant galaxy you aimed for would have evolved into something completely unrecognizable, perhaps a massive elliptical galaxy, or maybe nothing at all if it was consumed by a neighboring galactic cluster. The physics of what happens to matter at light speed provides another window into why this cosmic speed limit exists. As you approach light speed, your mass increases according to the Lorentz factor. This isn't just theoretical. Particle accelerators must account for this mass increase when calculating the magnetic fields needed to steer high-speed particles. At 99.999% light speed, a proton's effective mass increases by a factor of over 200. Push even closer to light speed, and this factor approaches infinity. This mass increase has profound implications for the structure of matter itself. The electromagnetic forces holding atoms together would be overwhelmed, chemical bonds would shatter, even atomic nuclei might not survive the extreme conditions. Matter as we know it cannot exist at light speed. Only massless particles like photons can achieve this ultimate velocity. This suggests that consciousness, which appears to require complex arrangements of matter, is fundamentally incompatible with light-speed travel. But what about the cutting-edge physics that might offer loopholes? Alcubierre's warp drive, proposed in 1994, suggests a method of faster-than-light travel that doesn't violate relativity. By contracting space in front of a spacecraft and expanding it behind, you could surf a wave of warped spacetime to your destination. The spacecraft itself never exceeds light speed locally, but the bubble of warped space can move arbitrarily fast. The energy requirements for an Alcubierre drive, however, make our earlier discussions of antimatter engines seem quaint. Initial calculations suggested you'd need more energy than the mass energy of the entire observable universe. Refined calculations have reduced this to merely the mass energy of Jupiter, but that's still far beyond any conceivable technology. Moreover, you'd need exotic matter with negative energy density, something that may not even exist in nature. Wormholes offer another theoretical possibility for bypassing the light speed limit. These shortcuts through space-time, first proposed by Einstein and Rosen, could connect distant regions of the universe. Travel through a wormhole wouldn't require exceeding light speed, but rather taking a cosmic shortcut. The catch? Wormholes, if they exist at all, would likely collapse instantly unless held open by exotic matter with properties that violate known physics. Recent work in quantum gravity, including string theory and loop quantum gravity, hints at even more exotic possibilities. Extra dimensions beyond the familiar 3 of space and 1 of time might allow for shortcuts that bypass the light speed limit. Brainworld scenarios suggest our universe might be a 4-dimensional membrane floating in a higher dimensional space. Perhaps consciousness could somehow access these extra dimensions, achieving effective, faster-than-light travel by taking paths unavailable to ordinary matter. The search for tachyons, particles that always travel faster than light, continues in laboratories around the world. If tachyons exist, they would have imaginary mass and experience time in reverse. Sending a tachyon signal could in principle allow communication with the past, creating causality paradoxes that make physicists deeply uncomfortable. Despite decades of searches, no evidence for tachyons has been found, suggesting that nature has indeed imposed an absolute speed limit. The philosophical implications of light-speed travel touch on the deepest questions of existence. If you could travel at light speed, experiencing no time, would you still be conscious? Consciousness seems to require change, the flow of thoughts and experiences through time. In a timeless state, could awareness exist? Or would you simply cease to be during your journey only to resume existence upon deceleration? Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the collapse of the wave function, the process by which quantum possibilities become classical realities. If consciousness cannot exist at light speed, this might explain why massless particles like photons can achieve this velocity. They exist in a purely quantum state, never collapsing into classical existence until they interact with matter. The anthropic principle, the observation that the universe's physical constants seem fine-tuned for the existence of conscious observers, takes on new meaning in this context. Perhaps the light speed limit isn't just a quirk of relativity, but a fundamental requirement for consciousness to exist. A universe where matter could achieve light speed might be a universe where complex structures, life, and awareness are impossible. As we push deeper into the realm of light-speed physics, we encounter phenomena that challenge our most basic assumptions about reality. The universe at light speed isn't just strange. It's fundamentally incompatible with existence as we understand it. Consider what happens to the electromagnetic force, the interaction that holds atoms together and makes chemistry possible. At light speed, the electromagnetic field itself undergoes radical transformation, compressed into an infinitely thin plane perpendicular to your direction of motion. This means that atoms, molecules, and all the complex structures built from them simply cannot exist in any recognizable form at light speed. The delicate balance of forces that allows electrons to orbit nuclei, that enables chemical bonds to form and break, that permits the intricate molecular machinery of life to function, all of this collapses into impossibility. You wouldn't just be traveling at light speed, you would cease to exist as a collection of atoms and become something else entirely, something our physics cannot adequately describe. Recent experiments at the relativistic heavy ion collider have given us glimpses of matter under extreme conditions. When gold nuclei collide at 99.99% light speed, they create a quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang. The temperatures reached exceed 4 trillion degrees Celsius, hot enough to melt protons and neutrons into their constituent quarks. This offers a preview of how matter breaks down under relativistic conditions, though still short of true light speed. The quantum mechanical implications become even more bizarre. The uncertainty principle, formulated by Werner Heisenberg, tells us that we cannot simultaneously know both the position and momentum of a particle with perfect precision. At light speed, where your momentum would be infinite, the uncertainty in your position would become zero. You would exist at every point along your trajectory simultaneously, smeared across the entire path from origin to destination. This connects to one of the deepest mysteries in quantum mechanics, the measurement problem. How does a quantum system in superposition collapse into a definite state? Some interpretations suggest consciousness plays a role in this collapse. But if consciousness cannot exist at light speed, and if light speed travel creates a superposition of positions across your entire path, we face a paradox that goes to the heart of quantum mechanics itself. The cosmic microwave background radiation, that faint afterglow of the Big Bang discovered by Penzias and Wilson, would transform into a wall of infinite energy in front of a light-speed traveler. This radiation, normally at a temperature of 2.7 Kelvin, would be blue-shifted to infinite frequency and energy. The gentle bath of primordial photons that fills all of space would become an impenetrable barrier, a cosmic wall that enforces the universal speed limit. But let's consider for a moment the informational aspects of light-speed travel. Information, as we understand it from Shannon's theory and its quantum extensions, requires distinguishable states and the ability to transition between them. At light speed, where time stops, no transitions can occur. No bits can flip, no quantum states can evolve, no information can be processed. You would become informationally frozen, a static pattern unable to change or evolve. This has profound implications for any science fiction dreams of uploading consciousness to computers and sending it across the cosmos at light speed. Even if we could somehow encode a human mind in photons or electromagnetic waves, that pattern would be frozen during transit. The rich dynamic process we call consciousness would be suspended, waiting to be reconstructed at the destination. You wouldn't experience the journey any more than a fax experiences its transmission. The holographic principle, emerging from black hole thermodynamics, suggests that information is fundamentally limited by area rather than volume. At light speed, where one dimension collapses to zero, the information content of any system would be radically constrained. This might explain why only massless particles can achieve light speed. They carry minimal information, just enough to specify their energy and polarization. Recent advances in quantum information theory have revealed deep connections between entanglement, space-time, and gravity. The ADS-CFT correspondence, a remarkable duality discovered in string theory, suggests that gravity in a volume of space is equivalent to a quantum field theory on the boundary of that space. At light speed, where spatial dimensions collapse, these dualities might reveal new physics we haven't yet imagined. The possibility of closed time-like curves, paths through spacetime that loop back to their own past, becomes relevant at extreme velocities. General relativity permits such curves in certain exotic spacetimes, like the region near rotating black holes or in universes with specific topologies. If you could somehow achieve light speed, you might find yourself not just frozen in time but caught in temporal loops, experiencing the same moment for eternity. The arrow of time itself becomes problematic at light speed. We experience time as flowing from past to future, a direction seemingly set by the increase of entropy described by the second law of thermodynamics. But at light speed, where no time passes, entropy cannot increase. You would exist in a state of perfect thermodynamic equilibrium, unable to perform work, unable to think, unable to change. This connects to deep questions about the nature of time itself. Is time fundamental, woven into the fabric of space-time as Einstein suggested, or is it emergent, arising from more fundamental timeless physics as some quantum gravity theories propose? The impossibility of consciousness at light speed might be telling us something profound about the relationship between time, entropy, and awareness. The many worlds interpretation of quantum mechanics adds another layer of complexity. If every quantum event branches the universe into parallel realities, what happens to these branches from the perspective of a light-speed traveler? With no time passing, would all possible branches coexist in superposition? Would you experience all possible versions of the universe simultaneously? A godlike perspective that encompasses all of quantum reality? Experimental tests of these ideas push the boundaries of current technology. The Large Hadron Collider accelerates protons to energies where time dilation becomes significant, allowing physicists to study how time itself behaves under extreme conditions. Atomic clocks on GPS satellites must account for both special and general relativistic effects to maintain accuracy. These real-world applications of Einstein's theories give us confidence in the impossibility of light-speed travel for conscious beings. The cosmic perspective reminds us that we are already traveling through space-time at the maximum possible rate. It's just that most of our motion is through time rather than space. From this viewpoint, achieving light speed means redirecting all of your space-time motion into pure spatial motion, leaving none for temporal progression. You would become a purely spatial being, extended across space but frozen in time. The intersection of consciousness and light-speed travel brings us face to face with one of the deepest mysteries in all of science, the hard problem of consciousness. How does subjective experience arise from objective physical processes? This question becomes even more perplexing when we consider what happens to awareness at the cosmic speed limit. Neuroscience tells us that consciousness seems to require integrated information processing across billions of neurons, with thoughts emerging from patterns of electrical and chemical activity that unfold through time. At light speed, where time ceases to flow, these neural processes would freeze completely. The electrochemical cascades that generate thoughts, the synaptic transmissions that encode memories, the oscillating brain waves that seem to correlate with different states of consciousness, all would stop. Not slow down, not pause, but cease entirely. The physical substrate of consciousness would become a static sculpture, beautiful perhaps in its frozen complexity, but utterly incapable of generating the dynamic phenomenon we call awareness. Recent research in quantum biology has revealed that quantum effects might play a role in consciousness. Microtubules in neurons might support quantum coherence, as suggested by Penrose and Hameroff's orchestrated objective reduction theory. Some researchers propose that consciousness arises from quantum processes in the brain that connect to fundamental features of space-time itself. If true, this would make the incompatibility between consciousness and light speed even more fundamental, not just a biological limitation but a deep principle of physics. The integrated information theory of consciousness, developed by Giulio Tononi, proposes that consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. This integration requires causal connections between different parts of the system, connections that unfold through time. At light speed, with no time for causes to produce effects, integrated information would drop to zero. By this measure, consciousness would simply vanish. But what about the subjective experience of approaching light speed? As you accelerate toward the cosmic speed limit, time dilation would create an increasingly strange perceptual reality. External events would appear to speed up dramatically. The gentle orbits of planets would become frantic whirls. The stately rotation of galaxies would spin like cosmic pinwheels. The entire future history of the universe would begin to compress into your present moment. This compression of external time would create a kind of cosmic cinema where you witness the future of the universe playing out in fast forward. Stars would be born and die in what seem like moments. Galaxies would collide and merge in beautiful cosmic dances compressed into heartbeats. The slow expansion of space itself would become visible, with distant galaxies racing away at ever-increasing speeds. As you approach ever closer to light speed, this temporal compression would become extreme. The remaining lifetime of the universe, trillions upon trillions of years, would squeeze into your final moments of subjective time. You would witness the heat death of the universe, the evaporation of black holes, the decay of all matter, compressed into your last conscious instant before reaching light speed and freezing forever. This creates a profound paradox. From your perspective, reaching light speed would mean witnessing the end of everything, seeing the universe age infinitely in your final moment. Yet from the universe's perspective, you would simply freeze, becoming a timeless monument to the impossibility of light speed consciousness. Which perspective is real? Both and neither. Relativity teaches us that all reference frames are equally valid, even when they lead to radically different descriptions of reality. The quantum Zeno effect adds another layer to this paradox. This effect, confirmed in numerous experiments, shows that frequent observation can freeze a quantum system's evolution. A watched quantum pot never boils, as physicists say. At light speed, where you exist in a single frozen moment, would you become the ultimate quantum observer, preventing the universe itself from evolving? This seeming absurdity might be another way nature prevents conscious observers from reaching light speed. Recent discoveries about time crystals, structures that repeat in time rather than space, offer intriguing perspectives on temporal physics. These exotic states of matter, first created in laboratory conditions in 2016, show that time can have structure just as space does. But time crystals require periodic driving forces, impossible in the frozen temporal landscape of light speed. Even these temporal structures would cease to exist for a consciousness moving at nature's ultimate velocity. The relationship between entropy and consciousness provides another angle on this impossibility. The second law of thermodynamics states that entropy always increases, giving time its arrow and direction. Consciousness seems intimately connected to this entropic arrow. We remember the past, but not the future because the past had lower entropy. At light speed, where entropy cannot change, the thermodynamic arrow of time disappears, taking with it any possibility of memory, learning, or conscious experience. String theory and other approaches to quantum gravity suggest that space-time itself might be emergent from more fundamental structures. In some theories, space and time arise from the entanglement of quantum information. At light speed, where spatial and temporal relationships break down, we might be approaching a regime where space-time itself loses meaning, revealing whatever deeper reality underlies our familiar four-dimensional world. The ADS-CFT correspondence, one of the most profound discoveries in theoretical physics, suggests that gravity in a space is equivalent to a quantum field theory on the boundary of that space. This holographic duality might mean that a light-speed traveler existing on a collapsed spatial dimension would experience reality in a fundamentally different way, not as a being moving through space, but as information encoded on a lower dimensional boundary. Experimental tests of these ideas push our technology to its limits. Particle physicists study what happens to time when particles approach light speed, finding perfect agreement with Einstein's predictions. Astronomers observe distant galaxies receding at significant fractions of light speed due to cosmic expansion, confirming that time dilation operates on cosmic scales. These observations reinforce the fundamental barrier that prevents conscious beings from achieving light speed. The philosophical implications ripple outward into questions about free will, determinism, and the nature of existence itself. If consciousness requires time to exist, and if the universe's structure prevents conscious beings from escaping time through light-speed travel, what does this say about the relationship between mind and cosmos? Perhaps consciousness isn't just something that happens in the universe, but something fundamental to its structure, woven into the very laws that permit time, change, and experience. The cosmic implications of light-speed travel extend far beyond individual consciousness into the realm of causality itself, the fundamental principle that causes precede effects, that the past influences the future but not vice versa. At light speed, this orderly progression of cause and effect completely breaks down. Events that should happen in sequence become simultaneous. The very notion of before and after loses all meaning, creating paradoxes that threaten the logical structure of reality. Consider the famous tachyonic antitelephone paradox. If faster-than-light communication were possible, you could send messages into your own past, creating causal loops that defy logic. While we're discussing travel at exactly light speed rather than beyond it, similar paradoxes emerge. From your light speed perspective, With all of space contracted to zero thickness in your direction of travel, every point along your journey exists at the same location. You would be everywhere along your path simultaneously, creating a kind of spatial superposition that challenges our understanding of what it means to exist at a particular place. Recent experiments in quantum optics have demonstrated that photons, particles that always travel at light speed, exhibit behaviors that seem to transcend our normal understanding of causality. In delayed choice quantum eraser experiments, the decision to measure or not measure certain properties of entangled photons can seemingly affect the behavior of their partners in the past. These experiments don't violate causality in any practical sense, but they hint at how different the universe looks from a light-speed perspective. The concept of the light cone, fundamental to understanding causality and relativity, becomes singular at light speed. Your future light cone, representing all the events you could potentially influence, would collapse into a line. Your past light cone, representing all the events that could have influenced you, would expand to encompass the entire universe. You would become causally connected to everything, yet unable to influence anything, a cosmic observer, frozen at the boundary between cause and effect. This brings us to one of the most profound realizations about light-speed travel. It represents a phase transition in the nature of existence itself. Just as water transforms into ice at 0 degrees Celsius, matter and consciousness undergo a fundamental transformation as they approach light speed. But unlike the phase transitions we're familiar with, this one is forbidden by the laws of physics. The universe has erected an impenetrable barrier between the realm of massive objects and the realm of light. The holographic principle takes on new significance in this context. If all the information in a volume of space can be encoded on its boundary, then a light-speed traveler, existing on a collapsed spatial dimension, might experience reality in its most fundamental form. You wouldn't be moving through space, but rather existing as pure information on the boundary between space-time and something beyond our current understanding. Recent advances in our understanding of black holes provide another perspective on the light-speed barrier. The event horizon of a black hole represents a boundary in space-time beyond which nothing, not even light, can escape. From the perspective of an outside observer, time dilation causes objects falling into a black hole to appear frozen at the horizon, their final moments stretched to infinity. This bears a striking resemblance to what happens as objects approach light speed, another kind of horizon beyond which normal physics breaks down. The black hole information paradox, one of the deepest puzzles in theoretical physics, asks what happens to information that falls into a black hole. Stephen Hawking's discovery that black holes evaporate through quantum radiation suggested that information might be destroyed, violating quantum mechanics. Recent theoretical advances suggest the information is preserved, perhaps encoded in subtle correlations in the Hawking radiation. Similar questions arise for light-speed travel. What happens to the information that constitutes your consciousness when you reach the cosmic speed limit? The connection between gravity and thermodynamics, revealed through black hole physics, suggests deep links between spacetime, entropy, and information. The Bekenstein bound sets a maximum limit on the amount of information that can be contained in a given region of space. At light speed, where spatial dimensions collapse, this bound would be severely constrained, perhaps explaining why complex structures like conscious beings cannot exist in this regime. Quantum field theory in curved spacetime predicts that accelerating observers experience a thermal bath of particles known as Unruh radiation. The faster you accelerate, the hotter this quantum thermal bath becomes. As you approach light speed, requiring infinite acceleration, this temperature would approach infinity. You would be immersed in a quantum inferno, a seething bath of virtual particles made real by your extreme motion. The possibility of extra dimensions, suggested by string theory and other approaches to quantum gravity, offers tantalizing but ultimately frustrating hints about bypassing the light-speed barrier. If our universe is a four-dimensional brain embedded in a higher dimensional space, perhaps there are shortcuts through these extra dimensions. But even in theories with extra dimensions, the local speed of light remains an absolute barrier. The geometry might be more complex, but the fundamental prohibition remains. Recent observations of gravitational waves by LIGO and Virgo have confirmed that gravity itself propagates at the speed of light. The merger of two neutron stars observed in 2017 produced both gravitational waves and electromagnetic radiation that arrived at Earth simultaneously after traveling 130 million light-years. This observation rules out many alternative theories of gravity and reinforces the universality of the cosmic speed limit. The quantum vacuum, far from being empty, seethes with virtual particles constantly popping into and out of existence. These quantum fluctuations become increasingly important as you approach light speed. The Casimir effect demonstrates that these fluctuations can produce measurable forces. At relativistic speeds, the interaction with the quantum vacuum would become extreme, perhaps contributing to the impossibility of light-speed travel for material objects. The relationship between information, energy, and computation provides another lens through which to view the light-speed barrier. Landauer's principle shows that erasing information requires energy, establishing a fundamental link between information theory and thermodynamics. The Margolis-Levitin theorem sets a maximum rate at which quantum systems can transition between distinguishable states. At light speed, where no transitions can occur, no computation is possible. Consciousness, which might be viewed as a form of computation, becomes impossible by fundamental information-theoretic principles. As we venture deeper into the impossibility of light-speed travel, we must confront how this cosmic speed limit shapes the very structure and evolution of the universe itself. The fact that nothing with mass can reach light speed isn't just a quirky rule. It's a fundamental organizing principle that makes the cosmos as we know it possible. Without this limitation, the universe would be a radically different place, one where causality breaks down, where past and future lose meaning, and where the delicate processes that led to stars, planets, and life could never have occurred. Consider how light itself shapes cosmic evolution. When the universe was 380,000 years old, it underwent a profound transformation called recombination. Before this moment, the cosmos was opaque to light. Photons couldn't travel far before colliding with free electrons. When the universe cooled enough for electrons to combine with protons to form neutral hydrogen, light was suddenly free to stream across space. This cosmic dawn, captured in the cosmic microwave background radiation, marks when the universe became transparent and light could finally fulfill its role as the cosmic messenger. The finite speed of light creates what astronomers call the observable universe, a sphere centered on each observer, containing all the events that could have influenced them. Because light takes time to travel, we see distant objects as they were in the past. The James Webb Space Telescope observes galaxies as they existed over 13 billion years ago, their light only now reaching us after an epic journey across space and time. This cosmic light cone structure, impossible without a finite light speed, allows us to literally see the history of the universe laid out before us. But the speed of light does more than enable astronomical observations. It sets the scale for all electromagnetic interactions. The electromagnetic force, which holds atoms together and makes chemistry possible, propagates at light speed. If this were not true, atoms couldn't exist in their current form. The delicate balance between the electrical attraction of the nucleus and the quantum mechanical properties of electrons depends critically on the finite speed of electromagnetic interactions. Change this speed, and you change the very nature of matter. Recent discoveries about fast radio bursts, mysterious millisecond pulses of radio waves from distant galaxies, illustrate how the universe uses light speed as its fundamental communication protocol. These bursts, some originating billions of light-years away, carry information about extreme cosmic events like magnetar flares or neutron star mergers. The fact that these signals travel at exactly light speed, neither faster nor slower, regardless of their frequency or intensity, demonstrates the absolute nature of this cosmic speed limit. The expansion of space itself adds another layer to our understanding of light speed's role in cosmic evolution. While nothing can travel through space faster than light, space itself can expand at any rate. During cosmic inflation, the universe expanded exponentially, with distant regions separating faster than light speed. This isn't a contradiction. Those regions weren't moving through space but were carried apart by the expansion of space itself. Today, galaxies beyond a certain distance are receding from us faster than light speed due to cosmic expansion, placing them forever beyond our reach. This cosmic expansion, discovered by Edwin Hubble and recently shown to be accelerating, creates what cosmologists call the cosmic event horizon. Just as black holes have event horizons beyond which nothing can escape, our observable universe has a boundary beyond which we can never receive information. Objects crossing this horizon are lost to us forever, their light redshifted to infinity by the expanding space between us. The finite speed of light, combined with accelerating expansion, means we live in an island of observability in an infinite ocean of inaccessible space. Dark energy, the mysterious force driving cosmic acceleration, might be related to the quantum vacuum energy allowed by the finite speed of light. The uncertainty principle permits virtual particles to briefly exist, borrowing energy from the vacuum as long as they annihilate quickly enough. The speed of light sets the scale for these quantum fluctuations. Some theories suggest dark energy emerges from the cumulative effect of these fluctuations, though the calculated values disagree spectacularly with observations. The worst prediction in the history of physics, off by 120 orders of magnitude. The anthropic principle, the observation that the universe's physical constants seem fine-tuned for life, takes on new significance when considering light speed. If light traveled infinitely fast, electromagnetic interactions would be instantaneous, preventing the formation of stable atoms. If light traveled much slower, stellar fusion would proceed differently, possibly preventing the creation of heavy elements necessary for planets and life. The specific value of light speed appears optimized for a universe capable of producing complexity and consciousness. Recent studies of gamma-ray bursts have tested whether light speed might vary with energy, as some quantum gravity theories predict. Observations of photons that have traveled billions of light-years show they arrive simultaneously regardless of energy, confirming that light speed is constant to extraordinary precision. This constancy across cosmic distances and times reinforces light speed's role as a fundamental constant of nature, not subject to environmental conditions or cosmic evolution. The interplay between light speed and gravity creates some of the universe's most exotic phenomena. When massive stars collapse, they can form regions where gravity becomes so strong that even light cannot escape. Black holes. The event horizon marks the boundary where escape velocity equals light speed. Inside this horizon, all paths lead inward to the singularity, where our current physics breaks down. Black holes represent places where the finite speed of light creates absolute boundaries in space-time, regions forever hidden from external observation. Gravitational lensing, predicted by Einstein and spectacularly confirmed by modern observations, occurs because gravity bends the paths of light rays. Massive objects warp space-time, causing light to follow curved paths. This effect, which depends critically on light having a finite speed, allows us to map dark matter, discover exoplanets, and peer deeper into space than would otherwise be possible. The universe uses its own mass as a cosmic telescope, with light speed setting the optical properties of these gravitational lenses. The connection between light speed and quantum entanglement reveals deep mysteries about the nature of reality. Entangled particles exhibit correlations that appear to transcend the light-speed barrier, yet no information can be transmitted faster than light using entanglement. This subtle distinction between correlation and communication preserves causality while hinting at a deeper structure to reality where space and time might be emergent rather than fundamental. The ultimate impossibility of conscious light-speed travel forces us to confront one of the most profound questions in physics and philosophy. Why does the universe enforce this limitation so absolutely? It's not merely that we lack the technology or energy. The prohibition runs deeper, woven into the fundamental fabric of space-time itself. Every attempt to understand this barrier reveals new layers of cosmic architecture, suggesting that the speed of light isn't just a speed limit, but a cornerstone of reality's entire structure. Consider the role of virtual particles in maintaining this cosmic speed limit. The quantum vacuum bristles with particle-antiparticle pairs that briefly borrow energy from empty space before annihilating. These virtual particles become increasingly important as real particles approach light speed. The interaction between high-speed matter and the quantum vacuum creates a kind of cosmic drag, a fundamental resistance that grows without bound as velocity approaches c. It's as if the universe itself conspires to prevent anything with mass from reaching this ultimate velocity. Recent experiments at the Large Hadron Collider have pushed particles to 99.999999% of light speed. That's 11 nines after the decimal point. Yet even with the most powerful accelerators ever built, consuming enough electricity to power a small city, we cannot add that final infinitesimal fraction needed to reach true light speed. Each additional 9 after the decimal requires exponentially more energy, a pattern that continues literally to infinity. The connection between light speed and the nature of space and time becomes even more profound when we consider loop quantum gravity, one of the leading candidates for a theory of quantum gravity. In this framework, space itself is quantized at the Planck scale, roughly 10 to the negative 35 meters. Time, too, might flow in discrete ticks rather than continuously, with the Planck time of 10 to the negative 43 seconds representing the smallest possible interval. Light speed might emerge from these fundamental quanta of space and time, representing the maximum rate at which changes can propagate through the discrete fabric of reality. This quantization could explain why consciousness cannot exist at light speed. If thought requires changes in state, and changes require the passage of discrete time intervals, then the frozen time of light-speed travel precludes any mental activity. You wouldn't experience a smooth approach to light speed, but rather a series of increasingly lengthy freezes between thoughts, until the final thought before reaching C would last forever. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature abhors naked singularities, points where physics breaks down visibly to outside observers. Black holes hide their singularities behind event horizons, preventing the breakdown of physics from affecting the outside universe. Perhaps the light speed barrier serves a similar function, preventing conscious observers from reaching a state where the laws of physics cease to make sense, protecting the universe from paradoxes that would undermine its logical consistency. The measurement problem in quantum mechanics takes on new urgency when considering light-speed consciousness. The Copenhagen interpretation suggests that conscious observation causes quantum wave functions to collapse into definite states. But what happens when the observer cannot experience time? Would quantum systems remain forever in superposition? Would the universe itself freeze into a quantum limbo? These questions hint that consciousness and the flow of time are more deeply connected to fundamental physics than we currently understand. Recent discoveries in neuroscience add biological constraints to the physical ones. Thoughts arise from synchronized oscillations across billions of neurons, with different frequencies corresponding to different cognitive states. Gamma waves around 40 Hz seem particularly important for conscious awareness. These oscillations require time to propagate across neural networks. At light speed, with time frozen, neural oscillations would cease entirely. Consciousness isn't just difficult at light speed. It's definitionally impossible given our current understanding of how awareness emerges from neural activity. The integrated information theory of consciousness provides a mathematical framework for understanding why awareness requires time. Consciousness corresponds to integrated information, the amount of information generated by a system above and beyond its parts. This integration requires causal connections that unfold through time. The mathematics shows that at light speed, where causes cannot produce effects, integrated information drops to exactly zero. By this measure, light speed travel doesn't just freeze consciousness, it mathematically erases it. But perhaps the most profound insight comes from considering light itself as the fundamental mediator of electromagnetic interactions. Every force in nature has carrier particles, photons for electromagnetism, W and Z bosons for the weak force, gluons for the strong force, and hypothetical gravitons for gravity. These force carriers establish the maximum rate at which influences can propagate through the universe. Light speed isn't just about light, it's about the fundamental rate at which causes produce effects in our cosmos. This causality-based understanding reveals why faster-than-light travel would unravel the logical structure of reality. If influences could propagate faster than light, effect could precede cause. You could receive a reply before sending a message, be born before your parents met, or prevent your own existence through grandfather paradox scenarios. The universe maintains its logical consistency by enforcing an absolute speed limit on all causal influences. String theory offers yet another perspective on the light-speed barrier. In this framework, fundamental particles are vibrations of incredibly tiny strings in a 10 or 11-dimensional spacetime. The tension in these strings sets the scale for particle masses and interaction strengths. Light speed emerges naturally as the rate at which vibrations propagate along these fundamental strings. Attempting to exceed light speed would be like trying to make a guitar string vibrate faster than its physical properties allow. Not just difficult, but impossible. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that our three-dimensional reality might be encoded on a two-dimensional boundary. From this perspective, motion through three-dimensional space is actually the evolution of information on this two-dimensional surface. Light speed represents the maximum rate at which this holographic information can update, the cosmic refresh rate of reality itself. Observations of the most energetic particles in the universe, ultra-high-energy cosmic rays, provide natural experiments in extreme physics. These particles carry energies millions of times greater than anything achievable in human accelerators, yet they still respect the cosmic speed limit. The GZK cutoff, where cosmic ray protons interact with the cosmic microwave background, demonstrates that even nature's most powerful accelerators cannot break the light speed barrier. As we approach the philosophical crescendo of our exploration into light-speed travel, we must grapple with what this ultimate barrier tells us about the nature of existence itself. The impossibility of conscious beings achieving light speed isn't a flaw in the universe's design. It's a feature that makes consciousness possible in the first place. Without this cosmic speed limit, the delicate interplay of cause and effect that allows thoughts to flow, memories to form, and experiences to accumulate would be impossible. The emergence of consciousness from unconscious matter represents one of the universe's most profound phase transitions. Just as water molecules individually have no concept of wetness yet collectively create the phenomenon we experience as liquid, neurons individually have no awareness yet collectively generate the rich inner world of conscious experience. This emergence requires time for neural signals to propagate, for patterns to form and dissolve, for the dynamic dance of electrochemical activity that somehow gives rise to the miracle of awareness. Recent advances in our understanding of emergence and complexity reveal deep connections between consciousness, time, and the light speed limit. Complex systems exhibit emergent properties that cannot be predicted from their components alone. These emergent phenomena require interactions between parts, feedback loops that develop over time, and the ability for information to flow through the system at finite speeds. The speed of light sets the maximum rate for these interactions, establishing a fundamental constraint on how quickly complexity can emerge and evolve. The free energy principle, developed by neuroscientist Carl Friston, suggests that living systems maintain their organization by minimizing surprise and uncertainty about their environment. This requires constant prediction and updating of internal models based on sensory information. At light speed, where no new information can be processed, this fundamental drive of living systems becomes impossible. Consciousness might be understood as the universe's way of modeling itself, and this self-modeling requires the flow of time that light-speed travel would freeze. Consider how memory, essential to consciousness, depends on the arrow of time established by finite light speed. We remember the past but not the future, because information flows from past to future at speeds limited by c. This creates the causal structure that allows experiences to accumulate into memories, memories to inform predictions, and predictions to guide actions. At light speed, with no distinction between past and future, memory becomes meaningless, and without memory, consciousness as we understand it cannot exist. The quantum Darwinism interpretation of quantum mechanics, proposed by Wojciech Zurek, suggests that classical reality emerges from quantum superposition through a process of environmental selection. Only certain quantum states survive interaction with the environment to become the classical states we observe. This selection process requires time and the exchange of information limited by light speed. A consciousness frozen at light speed would exist outside this selection process, unable to participate in the emergence of classical reality from quantum possibility. The relationship between consciousness and observation in quantum mechanics becomes even more mysterious at light speed. The delayed choice quantum eraser experiments show that future measurements can seemingly influence past quantum states. Yet this influence never violates causality because it cannot transmit information faster than light. A light-speed observer existing outside normal temporal flow might perceive quantum mechanics very differently, perhaps seeing all possible outcomes simultaneously rather than experiencing the collapse to singular classical states. Recent discoveries in quantum biology suggest that life itself exploits quantum mechanics in ways we're only beginning to understand. Photosynthesis uses quantum coherence to efficiently transport energy. Bird navigation might rely on quantum entanglement in specialized proteins. Even human consciousness might involve quantum processes in microtubules within neurons. These biological quantum phenomena all require careful isolation from environmental decoherence, impossible to maintain at the extreme energies involved in light-speed travel. The anthropic principle gains new depth when considering the light-speed barrier. Not only are the fundamental constants of physics fine-tuned to allow atoms, stars, and planets to exist, but the specific value of light speed creates a universe where consciousness can emerge and persist. A universe with infinite light speed would be one of instantaneous interactions, where cause and effect blur together, where complexity cannot gradually emerge through evolution. The finite speed of light creates the temporal scaffolding necessary for the universe to develop self-awareness through conscious beings. The concept of cosmic natural selection, proposed by physicist Lee Smolin, suggests that universes reproduce through black holes, with physical constants slightly mutated in each offspring universe. Universes with constants favorable to black hole production would dominate the cosmic population. Since black holes require stars, and stars require finite light speed to function, this mechanism would naturally select for universes with light speed limits similar to our own. Consciousness might be an accidental beneficiary of this cosmic evolution. The simulation hypothesis, the idea that our reality might be a computation running on some cosmic computer, takes on new meaning in the context of light speed limits. Every computation requires time to process information, with fundamental limits set by the energy required to manipulate bits. The Margolis-Levitin theorem establishes a maximum rate of computation based on available energy. Light speed might represent the maximum clock speed of the cosmic processor, the fundamental update rate of reality's operating system. But perhaps the most profound insight comes from recognizing that the universe has evolved conscious beings capable of understanding why they cannot travel at light speed. This self-referential loop, matter organized by physical laws into patterns complex enough to comprehend those same laws, represents a kind of cosmic awakening. We are the universe's way of understanding itself, including understanding its own limitations. The journey to grasp why light-speed travel remains forever beyond our reach has revealed the deep connections between consciousness, time, causality, and the fundamental structure of reality. Each impossible attempt to imagine consciousness at light speed has illuminated another facet of what makes consciousness possible at sublight speeds. The barrier isn't arbitrary but essential, not a wall preventing our exploration, but a foundation enabling our existence. As we stand on Earth, made of atoms forged in stellar cores, looking up at stars whose light has traveled for years to reach our eyes, we participate in the cosmic dance of matter and energy, space and time, all choreographed by the finite speed of light. Our thoughts, flowing at their own measured pace through neural networks, represent the universe contemplating itself across scales from the quantum to the cosmic, all unified by the same fundamental constant that makes both stars and consciousness possible. What if we could travel 1 light year per second? If you are curious, check out the video on the screen. In this video, we imagine what you'd see if you could make the impossible possible and soar beyond physics through the deepest reaches of space, compressing the history of the universe into moments. It's a must-watch.